Hello there, Mr. Sutton here, bringing you the Algebra 2 6-5 lesson on properties of logarithms. This will be a one-parter if you're doing the honors, two-parter if you're doing the CP, and in this one we'll be evaluating logarithms using some properties of logarithms. These are going to be non-base 10 logarithms. And then another thing we'll be doing, the main feature of this, is we will be learning how to expand and condense some logarithmic expressions. As part of learning some new properties of logarithms, we're going to explore some old properties of exponents, which kind of makes sense because logs are really exponents when you get down to it. So pause the video and see if you can review and simplify these expressions using your exponent rules. All right, so let's see what happened here. On this first one, we have multiplication of bases. So that's going to be x plus y. We're just adding the exponents there. For this next one, this becomes b to the x minus y. And then this last one, we multiply the exponents. This is b to the x times y. So just to kind of sum up what's happening here, because this will be important, we have multiplication of bases becoming addition of exponents. Division of bases turns into subtraction of exponents, and exponentiation turns into multiplication. So we can actually apply the same sort of reasoning for some logarithmic situations. So I call these the big three properties of logarithms. For the first one, let's say that you have the log of a product. Well, we saw that up here multiplication turned into addition. So it is with logarithms. Multiplication becomes addition. So you can actually split this up into the log of x plus the log of y. And if you're not really sure that this works, I mean, just take a simple example. Let's say you have the log of 10 times 100. That would be log of 1,000. Now we know log of 1,000 by itself is really 3. If you split this up into log of 10 plus log of 100, that would be 1 plus 2, which is also 3. And kind of going the other direction, if you have the log of a quotient, log of x over y, you can make that into subtraction. You can make this into log of x minus log of y. And then last but not least, if you have log of x to the y, well, we saw up here exponentiation becomes multiplication. So what actually ends up happening in this situation is this y comes out as a multiplier times the log of x. Because the y kind of pops out of here, I like to call this one unofficially the pop-out rule. Now all of these, it's worth noting, work in reverse as well. If you have two logs being added together, you can multiply their inputs inside one big log. Subtraction, you can turn that into division. If you have a coefficient outside the log, you can pop that in as an exponent on whatever input's already in there. So it goes both ways. So where do these properties of logarithms actually come up in practice? Well, like any way of expressing an expression in multiple ways, there's a lot of different uses you could have for this, either solving equations or just simplifying things to make processes easier. But here's a specific one we can do. Let's say that we know some predefined log values. They're just handing us that the log base 2 of 3 is roughly 1.585 and log base 2 of 7 is roughly 2.807. Now, I mean, just handing us this, you might wonder, well, what's the chances of that? It turns out that back when these logs were first kind of invented, created, there was a giant book of just log values, and they used these things to actually do some heavy-duty arithmetic. That was the original use of it, but we've kind of come a long way since then now that we have calculators. But we can still kind of use this approach on some expressions. So here are 3 log base 2 expressions that we would not be able to do on a scientific calculator because those can't do bases other than 10 or e, but using our log properties and these predefined values, we can actually find these 3 values. The trick on all of these is to try to express your input as a product, a quotient, or a power, and then split it up using your various log properties. Then you can use these predefined values to kind of finish the problem on a calculator. So with that in mind, see how many of these you can find using those log properties. All right, so for part A, we already have a quotient, so we can turn this into log of 3 minus log of 7, both of those base 2. And log of 3 we actually know, that's 1.585. Log of 7 we know, that's 2.807. And this is just these logs in base 2, remember. It's different for different bases. But we can plug this into the calculator right away. So let me just do 1.585 minus 2.807, and that comes out to negative 1.222. All right, now for this next one, it wasn't really any of those three things, product, quotient, or exponent right off the bat, but we can split 21 up. And the key is to look at the numbers they gave us, 3 and 7. Like, how does 21 relate to 3 and 7? Oh, well, 21 is 3 times 7. So we can treat this as a product. And since it's a product, we can now use our property of logs where we have a product, where we add the two logs together. So log base 2 of 3 plus log base 2 of 7. This is kind of like the first problem we did, only now we're taking these two numbers and adding these together. So let me just go back to Desmos, and this is super easy. I can just change my minus to a plus here, and now I've got 4.392. Now for this last one, 49, how does 49 relate to 3 and 7? Well, it doesn't really have much connection at all with 3, but you might recognize that 49 is really 7 squared. And if we recognize that, we can use our pop-out rule to move this 2 out in front of the log. So we can write this as 2 log base 2 of 7. And now I can go to Desmos and do 2 times 2.807. So crunching those numbers on Desmos, let me just put a 2 times here, and that comes out to 5.614. So on those last couple of examples, we were actually expanding logarithms with the intention of substituting predefined values for them. On this problem, we're just expanding the logarithm just for kind of its own sake. And now we've got some variables instead of just constants. So the idea when you're asked to expand a logarithm, basically what they want you to do is break it up so that each log has only one constant or variable inside. You can't have any exponents inside. You can't have more than one variable inside. So this right now, ln of all this stuff, this is too much stuff inside. This 5, this x, this y, they all need to be split into different logarithms. Pause the video and see if you can figure out how to break that up using your properties of logs that you saw recently on those last couple examples. All right, so the top level thing going on here is we've got some division. So we have that log rule where division turns into subtraction. I can split this up into ln of 5x to the 7th minus ln of y. And now I've got some multiplication going on inside this first logarithm. So I can split this one up further into ln of 5 plus ln of x to the 7th. And we still have that minus ln of y kicking around out there. The last thing that we have to be mindful of is that we're only supposed to have one constant or variable inside. We're not supposed to have this exponent inside. So we're going to have to pop that 7 out in front of that ln of x. And that completes what we're trying to do with this expansion. So if you are doing the CP version of this course, we've got 2 more examples for you to do in just a moment. If you're doing the honors version of the course, you can just skip ahead to the next example. But if you're doing the CP one, try both of these out, and then we'll bring it back and see how you did on each of them. All right, so for this first one, we've got division again. We can split that up into subtraction. So log of x to the 6th minus log of y cubed. And now we can pop out the exponents on this one. So this will be 6 log x minus 3 log y. Moving over to this next example, now we have multiplication going on, so we can turn this into ln of x times ln of 5th root of y. And 5th root of y, that is really an exponent. That is the 1/5 power. So we can pop that out as a 1/5 ln of y for that second term. If you're taking the CP non-honors version of the course, this is the end of part 1 for you. Feel free to pause the video, do some expansion log practice sorts of problems, and then join us again when we start condensing these. So for this problem, whether you're continuing on or rejoining us from the Algebra 2 CP version of the course, We're going a different direction than those last few examples. Those last one, we started with a single logarithm and expanded it into different logarithms. Now we're starting with a bunch of them and trying to turn it into a single logarithm. Again, though, using our logarithm properties. We're just kind of going in reverse. So a little bit of a trick you might want to try, or a tip on this one, I would recommend that you pop your exponents in first before you do anything else. And then you can go about the business of turning addition into multiplication and subtraction into division. So pause the video and see how far you can go turning this into a single logarithm. All right, so hopefully you took my advice and popped that 3 in as an exponent on the 2. So that'll be log of 2 cubed for that middle term. And now I'm going to turn, again, addition into multiplication and subtraction into division. Now another way you could think about this is if you have any subtraction, you're going to end up with some kind of fraction because there's some division. If you have multiple subtractions, that can get a little confusing. So a little rule of thumb you can use is that inputs that have positive logs are going to end up in the numerator of whatever your condensed answer is, and inputs from negative logs are going to end up in the denominator since we have to divide when there's a negative log. So we're going to have a fraction. In the top of the fraction, we're going to have the 9 because that had a positive log. We're going to have times 2 to the third, which I can turn into 8 if I want, because that also had a positive logarithm. And now this subtraction, remember, turns into division, so we end up with a 3 in the denominator. And you can simplify this a little bit if possible. So this is really 9 divided by 3 would give us 3. 3 times 8 would be 24. So we can condense this ultimately to just log of 24. Now you always have to double check because sometimes if you have a constant at the end, you can actually simplify it further. If the constant is a power of your base. In this case, though, if you're asking 10 to the what power equals 24, there's not a whole number or even any kind of fraction that does that for you, so this one's done. So at this time, if you're taking the CP non-honors version of the course, we're going to do a couple more condense the logarithm practice problems just to make sure we've got the hang of it. If you're doing the honors version of the course, you can skip ahead to the final example. All right, so again, just getting a little more practice. If you're doing the CP version, pause the video and try each of these ones out, and then we'll bring it back together to talk about both of them. All right, so for our first one, let's pop in our exponents. So we're going to have log of x to the 9th minus log of w to the 1/3, which I can also call the cube root of w. And now since I'm subtracting these, I can turn the whole thing into division of the inputs. So this will be log of x to the 9th divided by cube root of w. Over for this one, part B here, let's pop those exponents in. So this will be log of 5 to the 4th minus log of 5 to the 3rd. And now let's turn addition into multiplication and subtraction into division. So we're going to end up with log of 2,000 times 5 to the 4th. So that whole thing goes in the numerator. And then we have this 5 to the 3rd going in the denominator. We can simplify this a little bit. And before you reach for the calculator, let's use some exponent rules. 5 to the 4th divided by 5 to the 3rd. Subtract the exponents, right? So that's really just 5 to the 1st. 2,000 times 5 to the 1st is 10,000. And since this is just regular log, I'm asking what do I have to raise 10 to get 10,000? Well, there's 4 zeros, so 10 to the 4th would give you that. So then the log of 10,000 is just 4. So if you can simplify it to a single number, it's always recommended you do so. For our final problem, we'll see a little application here. So for a sound with intensity I, and that's watts per square meter, I'll take their word for that, the loudness, L of I, of the sound in decibels is given by this function down here, where I sub 0 is the intensity of a barely audible sound, which is some very low number, and I is the actual intensity that you're plugging in. So this is all based on kind of comparing the intensity of your noise with some very quiet noise. And this formula tells us how many decibels the actual sound is. Okay. So what they want us to actually do here, they say an artist in a recording studio turns up the volume of a track so the intensity of the sound doubles. By how many decibels does the loudness actually increase? So just to kind of set the stage for what we need to do here that would allow us to use some log rules, we're basically asking what's the difference between, if we're doubling the intensity, we're asking for the difference between L of 2I and L of I. And then actually plugging those into our formula, that's 10 log, this is going to be 2I over I sub 0 minus 10 log of I over I sub 0. So this is the expression that ultimately we're supposed to work with. Pause the video, see if you can use your log properties to kind of condense this into a single logarithm, and then maybe use an assist from your Desmos scientific calculator to figure out how many decibels this comes out to. Alright, so one thing we can do that we didn't go over before, but you've always been able to do it. Since you have a common factor of 10 here, you are actually allowed to factor that out. So we can call this 10 and then log of 2I over I sub 0 minus log of I over I sub 0. And now since we're subtracting these, we can divide their inputs. But now if I'm dividing by a fraction, I can actually multiply by the reciprocal. So I can make this log of 2I over I0 times I0 over I. So this is really division. We're just multiplying by the reciprocal. Well, these I sub zeros are going to cancel out. This is just 2I over I, which is, the i's are going to cancel as well. So that's just log of 2 in there. So 10 log 2 is the number of decimals. That's how loud this thing is. Now, what is 10 log 2? Well, if you want to plug it into Desmos, that comes out to approximately 3.01. So 3.010 decibels. So that's the end of this one. Feel free to turn down the loudness on your computer after you're done with this. Until next time, Mr. Sutton signing off.